Okay, so let me do over here, K6, also 5 by 5 convolution. This will produce 24 by 24. We add the bias, we pass it through activation function, we get 24 by 24. Okay, suppose I call this C1 and call this C6. Okay, so obviously there are many. So all these kernels will be different, okay, so that they are enhancing the image in a different way, because if they were all the same, it wouldn't be, there would be no point to it, right? So the other question is, what should be these kernels, K1 through K6, okay? Should we pick them to be smoothing type of kernels like moving average or high pass or band pass? What should we do? And the answer is we don't do anything. We just create them randomly in the beginning. And using the training data, part of the goal of the back propagation will be to learn the kernel. Okay, so kernels will be learned via back propagation. So they become part of our model, as you will see. Okay, so this part over here is our first layer of CNN, convolutional neural network. Sorry, there's one part I missed over here.
Reducing the size.
Yeah, so then we do what is called subsampling. For example, what we can do is take the average of 4 neighbors. So this will reduce it to 12 by 12. Okay, then up to over here is what we call one layer of CNN. Okay, so to briefly explain the subsampling, okay, let's pretend the C1 produced a data 0.5, 0.2, 0.1, 0.6, and so on. Okay, so we can do what's called max pooling, where these 4 values will be replaced by the maximum, in this case 0.6. Or we can do min pooling. All of these 4 values will be replaced by 0.1. Or we can do average pooling, meaning add, divide by 4, so which in this case will be 0.7 plus 0.2 plus, so 0.7, 0.8, 1.4 divided by 4 would be what? 4 something? No, 3 something, right? 0.35 maybe? Anyway, this will be replaced by the average value of all of those. Okay. So in pooling, see, unlike convolution, we move the window 1 pixel to the right. But in pooling, generally we do not have an overlap. Theoretically, you can. So next time we will go to the next 4 values and take the average of those. Okay, because we're not sliding it by 1 pixel, the size gets exactly reduced in half. So this will be 12 by 12. Okay, so anyway, up to this point, hopefully it makes sense. So essentially we applied 6 convolutions, passed it through the activation function, added the bias before that, and then basically did a subsampling, for example, averaging of the 4 neighbors without sliding window, without overlap. So this will produce 6 12 by 12 features over here. Okay. So that's our feature map over here, is these 12 by 12. Okay. So then what we do is we have multiple layers of CNNs. The second layer is kind of interesting, and this is where quite a few people get confused. So let me show you the second layer. So in the second layer, let's pretend we decided to apply 4 convolutions to each one of the output of the first layer of CNN. Okay, so let's apply K1 of 2, and this will be again, let's say 5 by 5. Okay, so if I apply a 5 by 5 convolution to 12 by 12, what will it produce? 8 by 8. 12 minus 5 plus 1, right? 8 by 8. Then we will add a bias. And let me go through K4 of 2. And this is also 8 by 8. Okay, very similarly to here also, we will apply 8 by 8. Let me call it, yeah, we'll develop a better terminology once we, so anyway, for the time being, this is 5 by 5, this is 5 by 5, right? So K1 through K4. This is layer 2. So the superscript, let's pretend, is layer 2. Layer 2, right? Okay, and let me further index it because this is coming from the first feature map, so let me call it K11, K14. So this will be K44. Sorry, there were how many? 6 of those. So this will be 6461. So my question to you is, how many convolutions are we doing over here in this example?
24.
24 convolutions, because we're doing 4 to each one of these, right? So there are 24 convolutions over here. Okay, so then we've already added the bias to each one of those. So then what we do is we add. So this gets added over here. Then this was the first feature map over here. This gets added over here. So how many additions will we be doing over here?
6.
6 additions. So there are 6 additions going on over here. Okay, same way. Okay, I forgot the, no, I think this is fine. Okay, so then the last one. So again, 6 additions over here. Okay, so how many of these outputs will we get over here? 4 of these. Okay, then we pass them through activation function. Okay, and then we do the subsampling. Okay, so what was the size up to here? 8 by 8, right? As we add these 6 of these, the size will still be 8 by 8.
Yes.
Once we do the subsampling, then what will be the size? 4 by 4. So this one will be 4 by 4, 4 by 4, 4 by 4, 4 by 4. Okay, so now whatever we did from here to here is our second CNN layer. Okay, so let's pretend, and we can repeat this as many times as we feel like it. So let's pretend we stop now, right? Next thing what we do is we flatten it out. So this is called the flattening layer. Okay, so if I basically went through every row and start putting values in a column, how many values will this give me? 16, right? Then another 16, then another 16, then another 16. So what will be the size of the data over here? 64 values in our example, right? Okay, now let's pretend we go to the classification layer. So let's say we create 30 neurons in our hidden layer. Then neurons in the output layer. Okay, so this is basically our classifier. And those are our outputs. So that's how the architecture of a deep CNN looks like. Okay, so from forward pass point of view, it's extremely easy. Okay, why is it easy? Because convolution, like I said, is basically putting the matrix, multiplying it, sliding it. I'll show you the code, actual code, how to do that. So that's not difficult. That's one line of code. Okay. So in the beginning, the kernels will be initialized randomly. Okay. These kernels will be initialized randomly. Biases will be initialized randomly, right? All the weights over here, so there's a set of weights over here. There's a set of weights over here. Those will, in the biases over here, those will be initialized randomly. Okay, so forward pass is easy. We compute the convolution, we apply sigmoid or whatever to every input in the matrix, element by element. We do the subsampling. Then further we do convolutions, right? Anyway, and the last part is basically flattening it out and doing the classification. So that's not too bad. The hard part comes in, how do we program it such that not only with one line of code you can indicate create 2 CNN layers or create 10 CNN layers. Because there are now so many connections involved and so on. So next time I'll show you, in my opinion, the best object-oriented way to organize it so that we can easily duplicate. So we'll just create a class called CNN layer instead of a regular layer, which will have this type of data in it, which will be consisting of many of the individual layers inside it. So if we are a little bit smarter, we can organize it really very neatly. But the difficulty is the back propagation. Okay, once we start to do the back propagation, okay, up to here is piece of cake, because you already know. But the question is, when we back propagate, what happens to the kernels? Because see, previously weights were easy. They were simply multiplying the input and adding it, feeding it to the next part. So the derivative of the multiplication, for example, if I said S1 equal to W1 times X1 plus W2 times X2, and if I said, give me partial S1 over partial W2, what will it be? X2. Just X2, easy, right? But if I say now W or S is doing a convolution with some kind of a kernel in the forward pass, what's the reverse of it? What's partial S over partial K? So suppose this is C over here. So what's partial C over partial K? Because that's what we are interested in. If we can find the gradient with respect to the kernel, then it's easy. We'll go update the kernels by multiplying it with the learning rate, so it becomes easy, right? So that's where the challenge is. So next time, bring all the attention. We will do it nicely. And then you'll say, wow, this was pretty straightforward. It's not that complicated, okay? So anyway, try to finish the current assignment. And then your next assignment will be programming the CNN. But don't worry, I'll give you a lot of starting code so that in a short amount of time you can get it done.
The second, the subsampling, would be considered as feature map also? 4x4?
Yeah, that's called the feature map. So feature map is basically the last output of our fit.
Question